Moving on to our next presentation for today. This is a video-based presentation. I'm pleased to introduce Julian Kettle. He brings 30 years of experience in the analysis of metals and mining to his current role as Senior Vice President, Vice Chair Metals and Mining at Mackenzie, where he is he's responsible for senior stakeholder engagements and relationships. And since joining Mackenzie, I should say, not Mackenzie, but extremely there, he has carried out the role of Manager, Metal Market Services, Global Head of Metals Research, and Global Head of Metals and Mining Research. So thank you very much. Please start Julian's video.
First, I'd like to just start with a grand statement, and my energy colleagues always roll their eyes when I start with this, but it happens to be true, and that is the undeniable fact that the energy transition starts now with metals. If you want to generate, transmit, store, or use low carbon energy, you cannot do it without metals and an unbelievably large volume of metals to actually deliver that energy transition. And whilst you might think this slide that I'm showing now is a bit of a shameless plug for Wood Mackenzie, actually you can draw some very interesting conclusions in terms of where metal sits. So if you look at the bottom icons, virtually every single one of those icons represents quite significant metals consumption, demand, and supply requirements. Whether it's wind, solar, storage, EVs, CCUS, even hydrogen. And you might think that's quite surprising. Well, if you want to build green hydrogen capacity, you need significant volumes of platinum group metals. They're in short supply. If you want to create the other end of the value chain, so if you're looking at EVs, particularly EVs using hydrogen, you need a catalyzer to convert and create the energy for motion. So we are truly built for the energy transition. Now, what I'd like to do now is to talk to you a little bit about our base case view. We have different scenarios that we create at Wood Mackenzie. We have a base case view, we call it our Energy Transition Outlook, ETO. And you might think it's quite alarming because we're showing demand under a scenario that only delivers a 2.5 degree warming. Now, that's obviously not aligned with Paris. Why so? The reason that we have a 2.5 degree outlook for global warming is because that is what the policy currently in place and projected will deliver. It won't deliver a Paris-aligned trajectory. And even with the lower demand requirements resulting from a 2.5 degree ETO, we still have, for many mined commodities, substantial increases in demand. Now, for some commodities, we've got relatively low growth rates, but others, we've got very high growth rates. The very high growth rates on an annual basis over 10 years, battery raw materials, some of what you might call the energy metals. So we're looking at high single digit and in some cases low double digit growth rates. If we turn our attention to rare earths obviously critical in terms of delivering the permanent magnets for wind turbines and EV motors in particular, but not exclusively so. Very high growth rates are projected under our 2.5 degree warming. Within our base, the broader base metal set, we're looking at low single digit growth. And then for the bulk commodities, iron ore, thermal coal, finished steel, met coal, we've got either negative growth or very, very low growth. Turning our attention to what this means in tonnage terms, because of course it's always interesting to look at growth rates, but the industry is defined by tonnage, tons out of the ground. And it's quite interesting to see, even at the very low growth rates that we're projecting, it translates to substantial incremental demand. Take copper, for example. So the global copper market under our base case will grow by 5 million tons between 2020 and 2030. Take graphite, graphite will grow to a 3 million ton market, so very, very substantial. At the other end of the scale, you've got bulk commodities, so we see a reduction in thermal seaborne coal requirements. The same for iron ore. Now, you might think, why so when we have electric arc furnace, EAF furnaces or supply growing quite substantially? That's but simply because of a rising influence of scrap. So that you start to think about the circular economy. So even under our base case, we're starting to see disparate performances of different commodities. And of course, that's just the demand side. When we start thinking about the requirement for supply and the challenges around that, we like to express the challenge of supply as a supply gap. So what is this? This is essentially looking at our base case supply curve, and you'll know that in mined commodities, mine supply does not continue evermore because of grade decline and depletion. So over time, base case supply starts to decline. If we intersect that declining supply with rising demand and express it as a percentage of the market that is yet to be committed to, and express it as a percentage, you can see a variation in stress in the industry. So, for example, if you were to look at the left-hand side of the graphic, look at lithium. So around about 25% of supply that is required by 2030 has not yet been committed to. So that represents a massive investment opportunity. Take copper. We have around about a 20% supply gap, and so it goes on. So we have significant stresses in the industry and a significant requirement to invest. Now, this is a natural state of affairs. Taking a 10-year view, you'd say, well, look, it doesn't take you 10 years to develop a project. Therefore, you don't need to commit to develop supply on a 10-year basis. But actually, that argument is becoming flawed because lead times are extending for the development of mining projects, to a lesser degree, refining and smelting. But we're starting to see an intersect between the requirement for supply and lead times. So if we look at this analysis of lead times, you can see that for certain commodities, from initial feasibility all the way to full ramp up, you're looking at anywhere from 4 to 10 years. Now, of course, those commodities where you're looking at a 4-year lead time, you'd say, well, look, there really shouldn't be a problem. But of course, what we've conveniently excluded from this graphic is the discovery phase. Now, the discovery phase can add another 10 years to these timelines. So we really are starting to run into problems and an ability to deliver the tonnage that's required to deliver our base case ETO. That's one issue that the industry faces is extending lead times. And of course, the other issue that we have is increasing above ground risk related to ESG, environment, social and governance. Now, care of our Maplecroft cousins, so a sister company of Wood Mackenzie within the Vivas family, we can assess above ground risk and look at a whole range of quantitative metrics to determine what the risks are in terms of operating in a particular jurisdiction. We can always also project forwards. Now, it's quite interesting to see how this graph changes over time, because if I was to have presented this graph a year ago or 2 years ago, you will have seen that the areas in the orange, in particular, the dark orange, have become more extensive over the past 2 years. So risks are rising, not falling. And of course, you can see in the text, there are myriad risks that miners face in terms of developing projects. Now, why is this a problem? Well, firstly, it's a problem because the risks are changing. The second problem is that it's difficult to quantify risk. And of course, the last thing that miners and their investors want is uncertainty. If we were to take, for example, tax policy, two sure things in life, death and taxes. And of course, what we're starting to see is certain jurisdictions that have been mining friendly are starting to tilt towards much, much higher tax take. Now, what that does is it puts at risk and at jeopardy investments. You know, uncertainty and higher taxes means lower returns, which means that investors will shy away from actually investing in certain jurisdictions. The other thing that strikes you when you look at this graphic is that there are very few mining-focused places on Earth you can go to actually operate with low ESG risk. Essentially, of the major mining centres, it's only in Australia and Canada where you have low ESG risk. And of course, there is a desire to invest in these countries, but we can't exclusively invest in these countries. Not all the commodities are available in those countries. You can't change what's in the ground. But unfortunately, if you were to map where we are going to have to mine for commodities and operate, there is unfortunately a very strong correlation between high risk and where we need to mine. So again, that represents a huge challenge for the industry. Now, I've talked about our base case energy transition outlook, the 2.5-degree world. So let's imagine what the world looks like, certainly from a metals and mining perspective, when we start looking at what a Paris-aligned decarbonisation trajectory looks like. So firstly, what we want to look at is, what does this pathway look like in terms of decarbonisation? And again, courtesy of energy transition practice within Wood Mackenzie, we have outlined our base case ETO, 2.5 to 2.7 degrees global outcome. You'll see that we have carbon peaking around 2030 and then slowly declining, but essentially we don't achieve anywhere near a Paris climate accord. You can see the white line, which is the 1.5 degree net zero by 2050 or before scenario. So you can see that there is a massive requirement to take carbon out of the economy. And let's not forget that if we're thinking about carbon budget, we're already plus 1.2 degrees. We've only got 0.3 degrees to play with before we have reached the tipping point. Also quite interesting, it's not that long ago, but many people have forgotten about it, COP26, back in November in the UK. Now, one thing that is often said about COP26 is it was a cop-out because there was very, very little policy that was agreed, let alone policy enacted to drive decarbonisation. But what we've done is we've taken all the COP26 pledges and we've said, let's imagine if they were converted into policy, and policy within the next couple of years. And we believe that COP26 would deliver just better than a 2-degree outcome. So it doesn't achieve Paris. A whole range of other policies would have to be brought in force. So we're not there yet. Now, what does a 1.5 degree pathway look like in terms of the build out of green energy supply? So you can see your eye is drawn to the middle part of the graphic. So wind and solar need to more than double by 2030. The expansion by 2040 and 2050 is a quadrupling or a 5-fold increase. Now, if you think back to the original schematic I showed you, that's great for metals. Well, actually, it's great for metals, but it's also problematic because we're already struggling to develop the supply, and wind and solar requires huge amounts of mined commodities to be supplied. If we think about the hydrogen economy, I've already mentioned we need huge amounts of PGMs. So a massive expansion of green hydrogen and green ammonia will require a huge amount of catalyzer materials. If we think about nuclear power is far more metals intensive than conventional thermal power. And we've even under our relatively conservative view of nuclear, we're seeing a massive expansion there. So this is all great for metals, but then also represents a challenge. If we think about EVs, because of course we can all conceptualize EVs, look at the difference in the requirement for EV sales penetration under our base case versus our AET 1.5. To put some numbers around it, by 2030, we will need to be building and buying around about 63 million EVs a year. Just to put that in context, last year we built and bought 6.5 million EVs. So we need a 10-fold increase. Bring it back to 2025. By 2025, we need to quadruple the building and buying in EVs. And the question I would ask is whether you think that's plausible. So a quadrupling in the next 3 years, it's going to be a tough ask. And also you can see a bit of regionalisation in terms of where we believe the build out of plug-in EVs are going to occur. Now, of course, what we have to recognise is that EVs are far more metals intensive for certain commodities than internal combustion engine cars. A great one that's always used is that a high-end Tesla will contain 80 kilograms of copper, whereas a conventional ICE will contain 20 to 25 kilograms, and so it goes on. So huge driver from EVs, wind and solar. Now, what does it mean for the requirement for supply? Now, the light blue area represents our ETA requirement, and what we've done is we've added on the additional requirement that results from AET 1.5, and you can see the requirement absolutely explodes. And again, to set this in context, if we think about the copper market, it's around about a 24 million ton market. By 2030, under AET 1.5, we'd have to find another 8 million tons. For lithium, the lithium market would become a 3.5 million ton market if we want to align with Paris. It's currently a 500,000 ton market. We need to find $400 billion of capital investment. And I should point out, that is just to build the capacity. That's not to decarbonize existing capacity. That's just to deliver the metals. So a huge challenge for the industry to deliver this tonnage, particularly when you consider where the industry finds itself. And what do I mean by that? What I mean by that is the fact that at the moment, investors in mining companies want mining companies to redistribute dividend rather than invest in growth. Why so? Because they were burned during the last down cycle. So what they're saying is they're saying to their mining companies, we want you to exercise capital discipline. We want you to give us dividend and special dividend distribution and share buybacks, because we want to have our growth. We're not interested in 5 to 7 years time. We want our dividend now. Now, if you think about the investment cycle, and again, this is where we start to intersect with our power advocate colleagues. This graphic is not all encompassing. It doesn't represent 100% of global capex, but it's pretty close. And what you can see is that 2012 was the peak, where the industry invested about $120 billion. We then started to introduce high levels of capital discipline, very targeted capex, and so we reduced our capex to the low point in 2016 of about $40 billion. Since then, capex has effectively flatlined, and yet the narrative is there's an energy transition, there's a shortage of metals coming, there's a super cycle, and yet the industry hasn't responded. And the reason the industry hasn't responded is because investors are saying, I do not want you to tilt towards growth. I want you to give me dividend. If we look at the forward view in terms of base case committed capex is for a 90% reduction from the peak in 2012. Even from last year, we are going to see a reduction of 73%. So again, the question I would ask is, if we need to deliver ever greater volumes of material to deliver an energy transition, where's the capex? Is the industry tilting into the energy transition? Arguably not. I've also superimposed the requirement for capex to deliver our 2.5 degree outcome and also our 1.5 degree outcome. And you can see we start to get to very substantial capex requirements. And again, is the industry delivering that? The answer is no, not now. Is the industry likely to deliver that? Well, if you think about where the world is right now, it looks like the world is entering a significant economic slowdown. We've got rising inflation, falling prices, we have margin squeezes. So again, the question is it likely that miners are going to tilt towards growth rather than protecting dividend? The answer undoubtedly is no. If we start thinking about the midstream, we can talk about the requirement for mine supply, but what about the midstream? So again, what does an accelerated energy transition mean for the build out of battery capacity? Putting to one side whether you can supply the raw materials for the batteries, let's assume you can. We need to invest something like $350 billion in gigafactories. To set that in context, GM has announced its largest ever single investment, and it's investing $7 billion in gigafactories. 7. So that still means we're pretty close to $350 billion that needs to be invested by 2030. Question mark, is that plausible? Probably not. Then we have the challenge of high prices over the past year to year and a half, and the fact that we've got technology and scale reducing the manufacturing cost of batteries. So what does that mean? What that means is that the raw material component of batteries represents an ever greater proportion of the battery cost. So right now, 70% of the cost of the battery is the raw materials in it. And if we think about where mine commodity prices have been, what it's led to is rising battery costs, which represents a problem. Because if you think that in order for EVs to be truly economic and to really work, we need battery costs to fall to the magic $100 a kilowatt hour. So firstly, we've got battery costs rising, not falling. Then we have energy prices, electricity prices rising. Put the two together and it challenges the economics of EVs. So we have a problem. Then last but not least, to round off, what about China? What about security of supply? If we think about the desire that we have in the US, in Europe, in the UK, in Japan, in Australia, to secure homegrown supply or to have what you might call blue on blue or friendly supply of critical raw materials, we need to be worried because currently China owns 80% of the battery manufacturing capacity, 80% of the precursor capacity, around about 70 to 80% of the refining capacity. In nickel, you might think, well, actually, it's not as bad, but the growth in Indonesia is primarily from Chinese entities. If we think about mining, again, you might say, well, actually, it doesn't look too bad. But if you think about cobalt, China controls 50% of cobalt supply from the DRC. If you think about Indonesia, China controls 90% of the nickel coming out of Indonesia. So, as they say, we should be afraid, we should be very afraid. Or another analogy I like to use is we have an energy transition raw materials restaurant. Currently, China is sitting at the table, eating its way through the dessert. We in the West are sitting in the taxi, reading the menu. We need to accelerate our investment in mining, or we will not be able to deliver our energy transition. And with that, I'll end what I've got to say. I believe there's some questions that the audience might have, and I'm happy to take questions.
Thank you very much, Julian, for that excellent presentation.